Hello. In this problem, we are going to evaluate the equilibrium composition and the equilibrium flame temperature of methane burning with air. Well, we get started by launching a test step. In this case, we'll assume it's a steady state combustion chamber. So we go to the open specific branch and launch the chemical equilibrium test step. And the model we are going to use is the IgE mixture model. Go to the HTML5 page and the app is launched. So first of all, in the composition panel, we set up the reaction. In this case, we have methane reacting with a theoretical amount of air. So option 1B will take you with for excess or deficient air, and the theoretical amount is given by 100%. That is the correct amount of air. If it's excess air, we can put the percentage here. If it's deficient air, we can put less than 100%. So clicking the execute button. Oh, we have to add methane to the mixture, and then we click the execute button to get the fuel and oxidizer in the right proportion. So this is exactly 1 kilomole of methane reacting with the correct amount of air to produce combustion products. Well, so fuel and oxidizer are set. To set the products, we go to the products panel, and then we need to choose what kind of species are included. And they must cover the following atoms because they're in the reactants. These are present in the reactants: carbon, hydrogen, oxygen, and nitrogen. We could go one by one, like CO2, CO, etc., like a designer product, or we can just select typical combustion products. So that selects the typically found in equilibrium combustion, and we add those. That's quite a list of products here. Of course, you can add or subtract more species if you want to. So we want to balance this reaction. These are the products, and we don't know their amounts. And the way the chemical equilibrium program works in this case, it minimizes the Gibbs function for the combination of the mole of the product species. That will minimize the Gibbs function of the system for a given pressure and temperature. And that will give us the equilibrium composition. Okay, so the next step is to go to the state panel, set it up. We have, reactants are key to state 1, and state 2 will be product. So we go to state 1. Let's assume that pressure and temperature are atmospheric. They're coming at 298 Kelvin and 100 kPa. And that calculates the reactants, in this case methane and oxygen and nitrogen, in the proportion as they appear in air. These are the reactants. The state is known. Now we'll go to the products. And let's say we just assume a temperature. Let's say we say pressure is the same, equals P1. And let's say temperature is, let's say, 2000 Kelvin. All right, so we calculate the state based on 2000 Kelvin. And you will notice the species for each component of the products. Informations are found, the amounts are found. You can go back to the composition panel and you can see it in a pie chart, and you can see the bulk of it is of course nitrogen, and H2 and CO2 are the complete combustion products, but there is some CO. If you put the pointer over CO, you can see it's 0.003, very little amount, and many other species in trace amounts are present here. Well, also notice that the reaction is completely balanced as shown by this check mark. All the compositions, the amount of product species have been mentioned here in the balanced reaction. Now, the 2000 Kelvin that we assumed as the exit temperature, is that the adiabatic equilibrium flame temperature? Well, to figure that out, let's go to the I/O panel and calculate Q dot in, as the amount of heat going in would be m dot 1 star H2 minus H1. Suppose we're heating the combustion chamber, then of course this difference will be the amount of heat that we are putting in. If it's really adiabatic flame temperature, there is no heating going on, and Q dot in should be 0. But look, Q dot in is negative. That means heat is coming out of the combustion chamber, which means we are cooling actually instead of heating, because the flame temperature that we assumed is a little bit too low. So let's increase it. Let's make it 2500. Redo the composition. So everything is now recalculated. The product's composition and enthalpy. Go back to the I/O panel. And notice that it was negative. If we calculate the amount now, it's positive, which means positive means that we are now hitting the mixture. In other words, to get 2500 at the exit, not only combustion is taking place, but we have to add heat. So obviously the correct adiabatic flame temperature, adiabatic equilibrium flame temperature, lies between 2000 and 2500. We are supposed to really do H2 equals H1. That should give us the correct answer, but notice that here we don't have this ability yet. So we have to keep on guessing the temperature of the exit temperature and recalculating the heat transfer. When the heat transfer is 0, we have found the adiabatic equilibrium flame temperature. Well, so let's guess 2200. Calculate the product's composition, go back to the I/O panel, and notice now if I calculate, this number is a little bit smaller, but still now it's negative. So we got to do, guess again. And if you continue this, so if we continue further refining our guess, we'll see that around 2225, temperature of 2225 Kelvin, when you calculate, this quantity is really small. Q dot is negative 145, which is nothing in percent term compared to how much heat transfer is going on when you first guessed 2000 Kelvin. So this is pretty close. The adiabatic equilibrium flame temperature is 2225 Kelvin, 2225 Kelvin, and the composition in the composition panel is shown. Of course, we could run a different what-if scenario. That suppose we assume there is what is the influence of, say, having carbon monoxide in the composition. If we could just click and remove it and redo the entire calculation. For instance, you can go and say, okay, calculate the products based on there is no CO being there. Well, in that case, composition is determined. Of course, that's not correct. If we calculate here, you'll notice that it's not at all the adiabatic now. There's a large amount of heat transfer, a negative Q dot in, which means heat might be lost. So this is the way we can carry on different scenarios, that what are the possible products in the combustion after combustion. By including enough species and then eliminating one by one, we can figure out which species are most important to influence the flame temperature, which are the dominant species.